Okay, so let's talk about the existence and uniqueness of solutions to differential equations. So here is an initial value problem. I've got this differential equation and this initial condition. And so what I'm trying to do here is illustrate some examples where we have a differential equation with an initial condition, and maybe there doesn't exist a solution, or maybe there exist multiple solutions. So for our first example, the problem is pretty fundamental. The issue here is that our initial condition is talking about plugging in x equals 0. So this 0 isn't the problem. This 0 is the problem. This is telling me that x equals 0, and my differential equation is just something that would be undefined when x equals 0. So there could never be a function y of x that satisfies this, because this would be telling me that the derivative of y is supposed to be something that is undefined. So I would never say that a function satisfies this. Another way of putting this is, and I'll talk more about this in just a second. Of course, this is a simple differential equation. Like, if I ignore the fact that we have an initial condition that doesn't really make sense, I can solve this. I can find a general solution, and that's just, of course, the antiderivative of this plus c. These are the first differential equations we ever learned how to solve. And anything like this, any solution of this form, is undefined when x equals 0, because you can't do the natural log of 0. Anyway, let me not talk about this example too much, and let me move on to the next example, which is a little bit more subtle. It's not necessarily so immediately obvious that there's going to be an issue with this. We have a differential equation, we have an initial condition, but nothing about the initial condition is telling me that I would be dividing by 0 or doing something undefined. And also that there's a different issue that's going to come up here. So, alright, so without thinking about it too hard, let's approach this the way we would approach it, because we learned how to solve separable differential equations, and this is separable. So for separable, we're going to separate dy from dx. So first of all, let me write y prime as dy over dx. And okay, I'm going to keep my dy on the left, move my dx to the right, and let me try to do everything at once here. I want to use multiplication or division to move any x's over on this side of the dx, so this x would be on the wrong side. So let me divide by x. This y is on the wrong side, so let me divide by y. And let's see, this 2 could, I could keep this 2 where it is or move it to that side. Let me just keep where it is. And I need something on the top of this fraction, so let me just put a 1 there. Okay. Variables are separated. Integrate both sides. We got this. We got this. Right. Okay, so let's get an explicit solution. Of course, this is implicit because it's not solved for y. So I'm going to do e to both sides. And let's get rid of the absolute values. Okay, this is kind of ugly, though. Let's simplify this. First of all, I can separate this, like the addition going on in the exponent, that's like e to the c. And here, so I could write e to the 2 ln absolute value of x. When I see e in a natural log, I know that there's some simplification that can happen here. But there's this 2 in the way. What I'm going to do with this 2 is bring it up. At this point, since this is absolute value of x squared, this is an even power. So actually these absolute values aren't doing anything anymore. So this is just natural log of x. The absolute value of x squared is the same as x squared. And then also when I have e to a natural log, those just cancel. So this is, here, I'm going to do a few things at once. First of all, let me do what I just said. This whole thing just turns into x squared. And this, I'm going to do the trick where we rename this a new constant. Let me just call that whole thing k. So like k is plus or minus e to the c. Okay, so there we go. I guess we have an initial condition which should tell us what k is. So I put in 1 for x, 1 for y. Oh, yeah, and this is supposed to equal 1 because I'm putting in 1 for y. So k equals 1. So our solution is y equals x squared. But wait, there was supposed to be a problem. I brought this example up because I wanted to illustrate how problems can come up. So what is the problem? The problem is the solution that we came up with is not really valid for the whole real line, like for every value of x. What do I mean by not valid? I guess I mean not unique. We could also have, let's say, I could have a piecewise function that's like x squared if x is greater than or equal to 0. And what I'm going to write is, yeah, what should I do? Here, maybe I'll call this like k naught x squared. So this is a piecewise function where k naught could be any constant. And okay, so let's talk about this. Let's check this. This function, which doesn't agree with the solution that we found, of course it agrees as long as x is greater than or equal to 0, it's the same thing, x squared, x squared. But since k naught could be any constant, if k naught is something different from 1, then this and this do not agree for negative values of x. And yet, this is a solution to the initial value problem. We can check that. Of course, the initial condition is easy. Y of 1 is 1 because 1 is a positive number. So I would use this. I would get 1 squared. Sure enough, that's 1. And also, the differential equation part would be satisfied. Basically, that's because both of these pieces of this piecewise function are of the form from the general solution. And also, if you check, what does this look like? This looks like, of course, on the right side, for positive values of x, we just have, this is like y equals x squared. And then to the left of 0 for negative values of x, well, it depends what k naught is. If k naught is a large positive constant, then this will be a much steeper parabola. If k naught is a small positive constant, then this will be like a short, fat parabola. K naught could even be a negative constant, in which case this would be like on the left, we would sort of see like half of a parabola opening down. And I guess the important part to check here is, and I'm not fully checking this, I'm just sort of talking about this. if you check what the derivative of this is at 0, it is, like, it does still satisfy this, like y prime is 0, x is 0, oh, and also y of 0 is 0, so you plug everything into both sides and it just says 0 equals 0, and it's satisfied. So what happened, and how can we avoid this? I'm going to state a general theorem in just a second, and that'll be helpful. But before I do, one thing that should have made us suspicious is even though our initial differential equation doesn't have a problem if x equals 0 or if y equals 0, like we're not dividing by 0, if you look at some of the intermediate steps we wrote down, these steps don't make sense if you pass through the origin, like if x is 0 or if y is 0. Like when we divide, when we were separating the variables, we divided by x, we divided by y, and if x or y happens to be 0, that's against the law, right? We also wrote, of course, we wrote things in the intermediate steps involving like natural log of y, natural log of x. Those are also undefined if x or y is 0. So the quick way to describe how to be careful about this is when you have a general solution, it typically involves a constant, and this is no exception. If your solution is going to pass through a point, like in this case the origin, if your solution is going to pass through a point where you wrote down in your work steps where both sides of the equation would be undefined at that point, then basically you would need to recalibrate your solution with a new initial condition. Whatever solution you come up with only tells you something for the value of that constant on an interval that contains your initial condition. So our initial condition was for a positive value of x, and so the solution we get, we should only trust the constant k equals 1 is what we got. We should only trust that for positive values of x. And sure enough, when I put this more general solution down, it does agree for the positive values of x, but for the once you pass into the negative values of x, you would have to say all bets are off regarding what this constant might be. It could be anything. We would need another initial condition. Like if we had an extra piece of information that says like y of a negative value of x equals something, that would tell me what k naught is. Anyway, let me state these theorems. So if we have, this is a theorem that's going to guarantee the existence and uniqueness of solutions to initial value problems, so we can avoid situations like the examples we just saw. Say we have an initial value problem that tells me y prime equals some function of x and y with an initial condition. If it happens that our function f, this one, and its partial derivative with respect to y are both continuous on some rectangle, because these are functions of two variables, so they're defined in two dimensions. So a rectangle is like a region in the xy plane. If they're both continuous on a rectangle that contains the point AB, and the point AB is from the initial condition, and this rectangle contains AB in its interior, so that the point AB is not on the border of the rectangle, it's somewhere in the interior. So assuming that, this theorem guarantees that there exists some interval I containing the value of x from our initial condition, so that this is the same A. And this interval contains A and its interior, so A is not one of the endpoints of the interval. A is like firmly inside of this interval. Such that this initial value problem has a solution, and furthermore, that solution is a unique solution. There's not multiple solutions, which is defined on the interval I. So, knowing that theorem, we could have seen that these things were going to be trouble. First of all, this one, it's like my f of xy is just 1 over x. And that's not continuous on AB, because in this example, AB would be the origin. It's just 0, 0. And this is not continuous at x equals 0. So we should have known that there would, well, if we knew this theorem, we should have known that there would be trouble here. With this other one, well, the trouble is, I mean, the way this theorem is stated, you're given a differential equation that's solved for y prime. It's solved for dy over dx. And while this one isn't, it's not immediately obvious what the problem is going to be. Once you solve for dy over dx, you're dividing by x. And the issue is, since you're dividing by x, while this differential equation, like your f of xy would be, here, let me actually write it down. For application of this theorem, our f of xy would be 2y over x, right? Because this is supposed to be y prime equals f of xy, so that's what we're dealing with. And this is continuous nearby the initial condition that like when x is 1 and y is 1, that there's no problem here because we're not dividing by 0. But this is the thing about the rectangle. F and its partial derivative, in order to guarantee that there's a unique solution, it has to be continuous on a whole rectangle. And for this function, the rectangle could not go past x equals 0. It could not go to the left of x equals 0 because we do have a problem at x equals 0. And yeah, by the way, for this theorem, the interval I is always contained in like the x coordinates that are relevant for that rectangle. So if we are passing through a point where our f of xy is not continuous, then we shouldn't think that the solution is going to be unique. Anyway, let me wrap this up. Here is a theorem that is saying almost the same thing. It's just a little bit technically slightly stronger, but it's about first-order linear differential equations. Roughly speaking, like I said, this is a little bit stronger than the above theorem. It doesn't immediately follow from it for the linear case. It's a little bit stronger for the linear case, but roughly speaking, this is just saying what the above theorem says but specifically for linear first-order differential equations. So this is the standard form for a first-order linear differential equation. We've got our function p of x and q of x, and the requirement is just that if p and q are both continuous on an open interval I containing a, then this differential equation or initial value problem has a unique solution, and the part that makes this stronger was it's the exact same interval I, the same one where p and q are continuous.